In this lecture, we will continue the discussion on the one-way analysis of variance, discussion of the R2 factor, the slides that we skipped across rapidly at the end of the previous portion of this lecture series on Module 2, Lecture 9. And then we'll talk about repeated measures and a few other additional types of tests that we won't spend a great deal of time on. In addition, I'll add a little bit of new information that we've just generated in some of the research that I'm involved with in studying diabetic kidney disease to look at correlation. So let's switch to the slide set. And I'm just going to escape here to be able to tell you we'll start with slide 26 out of 57 in Module 2, Lecture 9. So I've pulled the title slide down here, so it is actually number 27, sorry, because this one now becomes 26. So we're starting at slide number 27 that we had skipped past in the previous lecture, referring to this R2 value that shows up, at least with this GraphPad Prism software package that I had mentioned to you and that we've seen a few times in this presentation. And let's see what this R2 value is about. We would see it in the ANOVA table, at least with this software package, as I had mentioned. So it refers to the fraction of the overall variance combining the groups attributable to the differences between the group means. So this is beginning to remind us of what the analysis of variance is looking at, is the variance that we see all together in this collection of data from all your treatment groups, including your control group, of course, attributable primarily to the difference between the group means or across the columns, or within your groups. In other words, you have poor data sets within one or more of your treatment groups that's creating such variance overall, or contributing strongly to variance overall, that you cannot justifiably or statistically, realistically, evaluate the data any further. Basically have to go back to the chalkboard to redesign the experiment and determine what's wrong with the data overall. Now sometimes you can fail an analysis of variance simply because you have no variance across your treatment groups as well. So I need to clarify that. Just because you don't get a significant p-value in your in your analysis of variance doesn't mean that you've got to go back and redo the experiment. It may be that there really is no statistically significant difference between one or more of the means across your treatment groups. You still can have tight data within each one, but you just don't have enough variance resulting from anything to be able to say that any of the sample data sets are possibly different from any of the others. So let's not always think of failure to pass, if you will, the analysis of variance, meaning that you've got poor data sets. I always emphasize that to help understand how the test is run. So let's continue with this, feeling for the R2 value. So it compares the variability between the group means with the variability within the groups. So again, this is an actual analysis looking at the variability as we had described, across the columns, across the treatment groups, or between the group means, and that within each of the groups. So a large R2 value means that a large fraction of the variation is due to treatment that defines the groups. So the larger the R, then the more likely that the significance will be between the treatment groups, that's the source of the variance, not within the groups. Sorry, let me reset my pointer. I lost it here with exiting and coming back. So this value is calculated from the ANOVA table and equals between group sum of squares divided by the total sum of squares. So in essence, then it's a bit of a ratio of the columns by the total sum of squares. And here, of course, I'm taking this from that software package, Prism, GraphPad Prism software. The few other programs calculate this value following the ANOVA, so a little sales pitch of their own built into their help, and they've got a real nice button, as I think I'd said before, you click on that it helps you to interpret your results from the analysis of variance. So for a continuous variable, are the group variances equal? This is an important question. So when the groups are compared on a continuous variable, equality of group variances should be considered. So this variance, simply the squared standard deviations, as you know, the S squared of the groups, should be somewhat equal. So this is, of course, reminding us that we're talking about statistically being not significantly different, or statistically the two of them, the difference between the two would equal 0. So this makes them somewhat equal, right? So practically speaking, if the total sample size is greater than 25, a lack of equal variances isn't a problem. So again, sample size does have an impact overall. So for a continuous variable, are these group variances equal? So as a rule of thumb, the assumption of equal variances is satisfied as follows. If the ratio of the largest to the smallest sample size is less than 4:1, and if the ratio of the largest to the smallest variance is less than 20:1. So these are some guidelines where you can go and look at some of the results of your statistical calculations to see if you're working with group variances that are equal with a continuous variable data set. And again, it's more being familiar enough with your data at this stage of the analysis, the statistical analysis, to justify drawing your conclusions, and of course, as always, to defend the statistical evaluation that you provide in the reporting of your data. So you justify the analysis, you interpret it basically, right, to draw your conclusions, and that in essence, by my definition at least, is your statistical evaluation of the data. Once you get your statistical results, significant difference here, significant difference there, once you start describing those, then you're doing the statistical evaluation in the way that I view it. You're taking your stats to evaluate your data, and that is a stepping stone into drawing conclusions that are sound conclusions directly linked and interrelated to the data, which of course comes from good experimental design, as we are emphasizing all the time. So if that ratio of sample sizes is greater than 4:1, so if you've got one group that's 40 and one group that's 10, you're at this 4:1. But if you've got one group that's at 50 and your smallest group has only 10, then you're greater than the 4:1 ratio of variances. The ratio of variances should be correspondingly smaller. So if you've got 50 in one group and 10 in another, then the ratio of your variance should tighten up. Rather than 20:1, it should be something like 15:1 or 10:1 to be really reliable, or much more difficult to defend if you do not have that. So in other words, small sample sizes, especially when being compared to large sample sizes, excessively large sample sizes, leads to problems in evaluation because you have such an imbalance of data points contributing to your calculation of variance, standard deviation, and contributing to the mean. So as you can see, these guidelines are quite liberal, and the assumption of equal variances is easily satisfied in most cases. So with a small sample size, however, or variances that are not equal by those criteria we just mentioned, can transform the data or omit the outliers, and that's what I'm going to show you in a while, and then ask the question again. So this is what I was saying, is that some of the data analysis, statistical analysis, can be cyclical. It can send you all the way back to experimental design, or it just may be within the mathematical analyses transforming or looking at the mean plus or minus 2 standard deviations of the away from the mean, and omitting the outliers before coming back into the analysis. So it's important to note that many computer programs give a formal test of equality of variances, such as Levine's test or Bartlett's test, and we read about Bartlett's test that is run in this procedure as part of the output for the t-test or the analysis of variance. So this software package performs both the Bartlett's test and it gives you the R2 result. The Bartlett's test not only gives you a feeling for equal group variances, but also is closely related to Gaussian distribution of your data. So it can be used in essence to pass that test of a normal distribution of continuous variable data sets, justifying using a parametric analysis, and also that you have equal variances. And we'll take a look at our flow chart in the end. This is the data set that we looked at last time. Now let's talk about one-way ANOVA with repeated measures on time. We will build on this discussion after we take just a moment to read this slide and use it as a segue to spend a little more time on at least parametric correlation tests. And that's because it is a repeat slide. We've seen this before. Paired measurements differ from correlation, as we had stated. So in paired measurements, the same variable is measured on the same subjects at different times or under different conditions. So the reason for redefining this, as we'll go on to see in this discussion, is that a repeated measures, even if it's on time, is a paired comparison. So that's very important. The distinction in correlation, two different variables are measured on the same subjects at the same time or under similar conditions. So I want to take you to a brief discussion of some data that we've collected. Ooh, out of focus there. From a study on a human population. Of course, we had IRB approval. We collected urine from these patients and had access to some of the clinical data on blood tests. So again, we had to have two variables. So one is urine and one is plasma, as we will see. So I'll switch to the document camera for this one. And start just with a quick view of a review article, Markers of Diabetic Nephropathy. And what we're interested in is the changes in the connective tissue in the kidney called glomerulosclerosis that occurs especially in diabetic nephropathy. And we're not looking at any marker present here. We're interested in a growth factor that stimulates the secretion of extracellular matrix proteins, TGF, transforming growth factor beta. And we measured this in the urine contributed by the samples, by the subjects, and a plasma measurement of glucose concentration that reflects persistent high blood glucose, this hemoglobin A1C. So I won't bother with you with much more information than that. I'll just zoom back. So this column is the TGF-beta, and this is the HB1AC. There were 3 groups. The group 1 shown here is the normal patients, a group 2 that were managed diabetics, and a group 3 that was unmanaged diabetics. And for each of the groups, you can see that I calculated the mean and the standard deviation. This would be for the far left column, and the mean and the standard deviation for the right column. So this is the mean and the standard deviation for the TGF-beta and for the HbA1c. And then the outlier calculation is plus the mean plus 2 standard deviations or minus 2 standard deviations. Same thing for the HbA1c, and I did this for each of the groups. Got the outlier numbers. And then in Microsoft Excel, I just used a conditional format. If you look under Tools, you can find conditional format, and you can put in the parameters. And I had it turn with a dark background with white letters if the values exceeded this or were less than this number. Obviously, we're not going to see any negative values over here. And then the same for the, I guess this would be for this column, obviously, and these for this column. So what we determined in our experimental design was that if either one of these on either side exceeded the outlier values, we would exclude the both data sets. So this is one stage of processing the data. You'll see that I called it the clean data. Again, I don't like using that term, but or manipulating the data as is stated in our textbook. And this is the graph of that data set. Again, each one of these dots scattered around out here, it's a scatter plot, represents, of course, one individual human subject. And in each of those human subjects, we measured 2 different variables, and we asked the question, as the plasma levels of HbA1c increase, what is the effect on TGF-beta? Is it a linear relationship? So we did the test of the Pearson's linear correlation or linear regression analysis, and I'll show you the results of that in just a moment. And of course, this is the line graph that is of the predicted values based upon the distribution of the other data. So we can see a clustering down here and then a dispersion as we move away. So we can almost predict that it probably is a linear relationship, but there may not be enough data points really to substantiate saying that we have a real clustering around this line. So if we do get a significant correlation, there's probably going to be some indicator that it's not a really strong correlation. There's something weak about it, and it probably is just sample size because these types of human data tend to be like that. Your normal values are going to be clustered on the low end, and then as you move on out, you're going to have patients that don't display these clinical parameters exactly the same, even though they might be at the same stage of type 2 diabetes. So somewhere in here are most of the values for the managed group, and out here are the values mostly for the unmanaged diabetic group. So such a small sample size showing this type of relationship is promising. All right, so that contributes to the biological plausibility of it. Was it significant? So I actually ran this one in Microsoft Excel. So did the regression analysis. You get a multiple R. This is the R squared, the correlation coefficient, not the R2 that we saw just on the previous slides. This is R squared correlation coefficient. So we see, any of you that are familiar with this should be at least 0.75. But you like to have 80 or 0.8 or 0.9. This is kind of a percent confidence, if you will, that the data sets are truly have a strong correlation. But we see here that there is an ANOVA that is processed as well on this data set, and get an ANOVA on the regression, a residual that we'll describe a little bit later when we talk about two-way ANOVA, and a total. So these are the degrees of freedom, the sum of the squares, the mean sum of squares, an F value, and the observed F value exceeded the critical F value, so it was really quite significant. So we do have a significant correlation, but we don't have a strong correlation coefficient, so there's something weak about this correlation, but it exists. So this gives us a type of data that, of course, is different when we just compare the mean TGF beta levels across these three patient groups. So I think you can see, obviously, normal, managed, and unmanaged. The effect size between the first two groups and the third group, the unmanaged group, is quite large, and we're in picograms per ml going from 25 up to 100, so a difference in effect size of close to 75 or more units. So that seems quite large. We can see in this unmanaged patient group, standard error of the mean is certainly larger than the standard error in the first two groups. The standard error of the mean isn't quite even a third of the mean for this group. But obviously, when we look at this, and you can see the asterisks already, we want to run a one-way analysis of variance on this type of data to compare the means, test for the variance, and that comes up significant. So here's where you see I labeled it the clean TGF data for the ANOVA, one-way analysis of variance. So that was the table analyzed. P-value less than 0.001. And then the summary on the p-values are the means significantly different with set at the critical value that we chose, p less than 0.05. Yes, gives the number of groups. Our F value, there's that R squared value, so 0.7396. That's pretty high, so it means that the variance is coming from the difference between the groups. We saw that just in looking at the graphs, right? Any variance contributed by each one of the treatment groups, even though we're looking at standard error of the mean, we know the standard deviation will be representative of this. The variance within each is not so great, but the difference between the groups would reflect a variance across the columns, the groups, and therefore we would expect a high R squared value here, the R2 that we had mentioned, and so there is a strong likelihood that there will be differences between the groups, and you can see down here, use the Tukey's multi-comparison test in this case. So the Bartlett's test was significant as well. Do the variances differ significantly? Yes, and of course that's due to the treatments. And then looking at the ANOVA table, we've got the treatment, a residual, and the total. As I said, we'll discuss this residual at a later time. So we have the sum of squares, the degrees of freedom, so the analysis of variance was significant. F, open parentheses, the treatment, 2, comma, total degrees of freedom, 44, close parentheses, equals 59.66 at p less than 0.001. So the analysis of variance was significant. And using the Tukey's multiple comparison test, we have normal versus managed, normal versus unmanaged, managed versus unmanaged. We predict that these two are going to be significant, but comparing the first two bars on that graph would not be. And here we see we predicted correctly the normal and the managed not significant, p greater than 0.05, and p less than 0.001 for the normal versus unmanaged and managed versus unmanaged. And of course, as well, provides the table of the mean, standard deviation, and standard error of the mean for each of these, so you can go back and take a look at them. And then the range, minimum to maximum, all the critical data points are here, and then the sample sizes. Eight times 4 is 32, so we're safe there, right? There's one other point that I wanted to make, but it's not coming to me at the moment. Okay, well, let's go back to the lecture. Oh, I know what the point was. Just come back here just a moment. So, the typical approach is with the asterisk. I didn't put the correct asterisk in there. If this was p less than 0.05, it would be a single asterisk. P less than 0.01 is 2. I put 2, it should be 3. 3 asterisks is P less than 0.001. So that standard should be followed. So I have an error on my graph based upon the standard approach to reporting statistics graphically, such as that. Okay, back to the computer, back to the repeated measures ANOVA. So we see a little comparison there with one data set on how we treat a correlation different from the analysis of variance, unpaired analysis of variance without repeated measures. Now let's go on and talk about repeated measures, get some definitions in here for this. So the repeated measures design is taking more than one measurement from each subject, animal, etc., cell set, whatever it is, but more than 2. So it's not just a paired comparison. So again, because we're doing the ANOVA with repeated measures, it's got to be 3 or more measurements on the same group. You may not be testing a couple different drugs or different concentrations. You're making more than 2 measurements on those groups. So, for example, one of the factors being studied is time, and a measurement on each animal and each treatment group is made for each time point. So this is and more than 2 time points, so it would be a one-way analysis of variance with repeated measures, and time being the variable on which you repeated the measures. So not only are you interested in assessing the overall effect of the treatment, but also the effect of time and the treatment by time interaction. So what this analysis performs, looking at this interaction, as we'll see and become more and more familiar with it, it's actually providing an assessment of a correlation between your data, right? So we are, but it's more of the effect. Is there an interaction, a correlation between the effect of the treatment and the repeated measures, in this case time? So it's looking at a correlation between your independent variables, not a correlation between two dependent variables or one dependent variable. Now let's just leave it at 2 dependent variables there so it doesn't get complex. As you saw in the previous demonstration, we really had 2 dependent variables. I couldn't change a person's HbA1c. The patient comes in, that's their value, so it really is a dependent variable. The independent variable was their categorization, which of course is not a parametric assessment. So it gets a little tricky there. But anyway, don't let it throw you off at the moment. So you're not only interested in assessing the overall effect of the treatment, but the interaction. So it does give you some feeling for the correlation between two of your independent variables. Remember, time is an independent variable. You can't change time, but you can allow time to pass. And then drug at different concentrations, or vehicle, zero concentration of drug, plus 10 milligram per kilogram, whatever, millimolar, are the two levels. So is there any interaction of that treatment with time or over time? So the second factor can introduce a real treatment condition other than time, for example, the dose level, but the analysis is going to proceed in the same way. So this repeated measures ANOVA has certain assumptions. It assumes the data are representative of a population. Remember, population versus sample, and how we establish that, basically random sampling and looking for ruling out bias. Each set of values, each row was selected independently, so there's assumptions of an assumption of independence that you can go and study up on if you want to make more sense from this. But this, remember, is being able to move values around without impacting all those means that we saw in the ANOVA table. The random component of the variable follows a Gaussian distribution, so it has to pass the normal distribution test. It's not important if the samples are large, because larger samples of continuous variable data have a greater tendency to be from normally distributed data sets, or normally distributed among the population. It's not necessarily a safe argument to continue analyzing data that do not pass this. If you're uncomfortable with it, consult a statistician by all means, certainly. Repeated measures ANOVA again assumes the matching was based on information available before the experiment was begun. Okay, so you've got to match your data. So your design has to be careful. If you're going to have a repeated measures, make sure you design it appropriately, and that the matching of your the samples from which you're collecting is based on information that you can come to know or predict reliably, as with the HbA1c, very well known, the population data is available to make a reliable prediction that in a chronically unmanaged diabetic patient the value is going to be high, that type of a thing. So you're going to match your patients based upon criteria that you establish before you go into the experimental procedure or execute the experimental design. The correlation between every pair of columns is about the same. You will violate this assumption. For example, I just want to go back, sorry about that. And of course, it's important to match, because that's the pairing of a repeated measures. Remember, the paired comparison has to be very careful. 2 measurements, but if you're going to get to 3 or more, then you want to be really careful that you get the matching taken care of before you initiate the experiment, because your data set will be all over, potentially can be all over the place if you don't get a good matching to start with. So let's do this again, sorry. The correlation between every pair of columns is about the same. You will violate this assumption, for example, if 2 of the columns represent control measurements and the other columns represent measurements during treatment. So you expect the values of the 2 control columns to correlate more closely than do the values in any other pair of columns. If you violate this assumption, the p-value will be too low. For more information on this assumption, look up compound symmetry in an advanced statistics book. So if you took 3 baseline measurements, your control values, and then started adding a drug, you could encounter situations where you would make errors in concluding that there was a significant ANOVA when possibly there isn't. So the paired and repeated measures test, when choosing a test, you need to decide whether to use a paired test called the repeated measures when you compare 3 or more groups, as we said. You should choose a paired or repeated measures test when the experiment used paired or matched subjects. And now let's take a look at some examples. I think I've confused this definition a few times throughout these lectures. Hopefully this will help to clarify it. It's easy to confuse kind of a cloudy arena of information when so many people do so many different types of experiments and can't be exactly certain how they want to process your data. Remember, with the paired comparison of just 2 groups, you really are going to look at the difference. So you have to calculate the difference between the 2 in order to make such an assessment. Maybe you want to compare the group means rather than the look at only at the difference between the 2 groups. Difference between individuals among the 2 groups. So for the 2 groups, you measure a variable in each subject before and after an intervention. You recruit subjects as pairs matched for variables such as age, ethnic group, and disease severity. One of the pair gets one treatment, the other gets an alternative treatment. You run a laboratory experiment several times, each time with a control and treated preparation handled in parallel. So this is what we were saying before, trying to come up with a type of experiment we might perform, like the boxes of seedlings put in the same location, but only one of those boxes in that exact same environment was exposed to the electrical field. So it was paired based upon matching the environment, not paired based upon making the same measure on the same data source or sample source at different intervals, or before and after a particular treatment. And so you may do a paired comparison if you are testing. Well, let's go on and see more examples. So you measure a variable in twins or child-parent pairs. For 3 or more groups, you measure a variable in each subject before, during, and after an intervention. So it is more than 2. You recruit subjects as matched set. Each subject in the set has the same age, diagnosis, and other relevant variables. So if you're doing cell cultures, have to be the same passage. You can't have one on an early passage and one on a late passage and expect to have comparable groups. That we recognize would be not only faulty assumption for paired comparison, but also introducing a bias based upon sampling error. So you recruit subjects as matched sets. Each subject has the same age, diagnosis, other relevant variables. One of the sets gets treatment A, another gets treatment B, and another gets treatment C. So you're still making a paired comparison across the groups. You run a laboratory experiment several times, each time with a control and several treated preparations handled in parallel. So this is the one where we were thinking about cell cultures or some type of living cells that you are growing, and they're both in the same incubator, so in the exact same environment. One is in your vehicle solution and the other has a drug or some type of chemical added to it. So that could be a paired comparison, or even one with repeated measures if you're making 3 or more measurements on them. You measure a variable in triplets or grandparent, parent, child groups, and so on and so forth. So the paired and repeated measures test, more generally, you should select a paired or repeated measures test whenever you expect a value in one group to be closer to a particular value in the other group than to a randomly selected value in the other group. That's kind of a mouthful, but you need this predictability, and what it's beginning to tell us is that with one-way analysis of variance and repeated measures, we're not going to be able to move data around very much. Remember, with the one-way layout, we could rearrange within a column but not across columns. Our columns were the different treatment groups, and the rows were the individual data points within a treatment group. Now what we're going to see is that it will be a bit different than that, and we don't have quite as much freedom to move things around. And that's basically what this is saying in a rather complex way. So ideally, the decision about repeated measures analyses should be made before the data are collected. Certainly, the matching should not be based on the variable you are comparing, because that's the one that you expect to vary the most to contribute the variance to get a significant effect. If you are comparing blood pressures in two groups, it is okay to match based on age or zip code, but it is not okay to match based upon blood pressure, kind of a prime example with the data point type of data that we're familiar with in humans. A repeated measures experimental design can be very powerful as it controls for factors that cause variability between subjects. If the matching is effective, the repeated measures test will yield a smaller p-value than ordinary ANOVA. The repeated measures test is more powerful because it separates between subject variability from within subject variability. So now with repeated measures, we want to make sure that the variability is coming from our within subject. This subject from here to here to here is causing the variability rather than the between the subjects at any one time point. So again, we're starting to look at this same approach of seeking out variance, identifying the source of that variance, and is it the source that's necessary to be able to lead us to conclude that there is a true difference somewhere that's specific for the relationship between the test factor and the outcome measure. So if the pairing is ineffective, however, the repeated measures test can be less effective because it has fewer degrees of freedom. So if you don't have the same number of subjects for each time point, if you've got dropout, obviously you can't have an equivalent pairing across all the time points. So the PRISM tests whether the matching was effective and reports a p-value that tests the null hypothesis that the population row means are all equal. If this p-value is low, then you can conclude that the matching is effective. If the p-value is high, you can conclude that the matching was not effective and should consider using ordinary ANOVA rather than repeated measures. So the p-value is calculated from the ANOVA table with repeated measures ANOVA. There are three sources of variability. Between the columns, that's your treatments. Between the rows, those are individuals, and a random one. So the ANOVA table partitions the total sum of squares into those three components. It then adjusts for the number of groups and the number of subjects, expressed obviously as the degrees of freedom to compute two F ratios. So now we're seeing two F ratios being computed. One F ratio tests the null hypothesis that the population means are identical. If we fail to pass that test, then we reject the null hypothesis, saying that at least one of the population means is different than the others. So if the calculated F ratio is greater than the critical, then we reject the null hypothesis. The other tests the null hypothesis that the row means are identical, and this is the test for effective matching. So in both cases, the F ratio is expected to be near zero if the null hypotheses are true. If the F is large, the p-value will be small, which is consistent with everything we've discussed so far. So let's look at a data set a one-way ANOVA with repeated measures. So in this case, there were a set of animals that were treated with a drug. This is back to that serotonin idea affecting I think this was blood pressure. Yeah, the change in the blood pressure. So it's a paired comparison. So we calculated the difference from baseline at these different time points subsequent to the injection. So the baseline, obviously, baseline minus baseline is 0, and then we have these changes over time. So here we have 1, 2, 3, 4, 5, 6. Oh, look, we didn't get measurements on 2 of them. I wonder how that'll affect things. But let's continue on. This is the way that the data was set up. So time is the single column. It's a factor X. And then each of the columns here are individual animals, obviously all paired. I think this was in the, what was in the SD tells me here it was Sprague Gully rats that had normal blood pressure. So this is the effect of this drug on decreasing blood pressure below normal in normal animals. So that was the, oh, and then I didn't show the right table for the when the table that was analyzed here was in the hypertensive rat. So look at that. You've got to be careful and read things closely. Anyway, in the hypertensive rat, the repeated measures ANOVA gave a p-value of 0.0003. So p is less than 0.001. Here we see the 3 asterisks telling us that. Are the means significantly different? Yes. The number of groups, there were 6. Here's the F value, the R squared. So that's still pretty high. Was the pairing significant? Yes, we see that here. So the pairing was effective, even though there were a couple missing data points. So that didn't impact the F value that much. And then the ANOVA table here, the treatment between columns, the sum of squared, degrees of freedom, mean sum of squares, individual, the between rows shown here, the residual shown there, and the total. So F, the one-way ANOVA with repeated measures. Sorry, I had that all covered up when I was pointing it out. The treatment, individual, and residual, and the total. So the one-way analysis of variance, one-way ANOVA with repeated measures on time was significant. Open brackets F, open parentheses treatment, degrees of freedom 5, total, comma 29, close parentheses equals 7.812, semicolon p less than 0.001. Close brackets. So that's how you'd report the significance for this type of a test. And then you see the Newman-Cool's comparison test down below that we pull up, and it compared all the groups. There's just a couple that are key as we're comparing this change over time. The 55-minute time point was the return to baseline. So return to baseline was considered the effective comparison, so that was p less than 0.01. So when we see the graph and look at the 35-minute time point subsequent to the injection of this drug, we'll see that that's the largest drop. There's a couple of other comparisons here, but the 25-minute, only the comparison to the 55 becomes important. So at 15 minutes, it's significant at the 0.05 level. And at the 5 minutes, it is not significant. And at 45 minutes, it's not significant. So we've recovered baseline. And that's what we see here. So at the 5 minutes on out through, we saw the significant differences from this value, which is, when we look at the raw data, is not statistically significantly different than baseline. So we recovered baseline at 60 minutes, so this difference is not statistically significant, however, these are. So at the 35-minute time point, this was the most significantly different data point. So the dose response is another form of evaluation that we've talked about, and typically an analysis of variance is used, although the trend test is the one recommended in one of our texts, the Selwyn. So let's take a look at this. So another common design is one in which increasing dose levels of a test compound are administered to different subjects, often including a zero dose or a vehicle control. So remember, a dose response is very important because it falls on, other than ruling out chance, to say that you've got significant data for the dose effect, a dose response falls under the biological plausibility. It's one of the criteria contributing to establishing a causal association. If you don't get this change in the magnitude of the effect with the change in the concentration of exposure, whatever it is, then you question whether it truly can be fit within a biological model. And whether it could be a causal association. So thinking about how you would assess a dose response is important statistically. So if the response to the compound is likely to be more severe with increasing dose, then tests for trend are more appropriate than an overall ANOVA. As I said, though, most people will use an ANOVA and haven't seen too much criticism of it yet. So such trend tests are often applied to the context of animal safety studies for new drug entities, like toxicological studies. You may also consider dose response studies in which the goal is not only to test for a treatment dose effect, but also to characterize the functional form of the dose response. So is it an inverted U? Is it U-shaped, inverted U-shaped, or S-curve shaped, whatever it may be? Is it truly linear? As long as there's a dose response and it fits one of the known models, we feel that we have a stronger case to claim a causal association between the test factor and the outcome measure. So in such cases, regression analysis models and methods can be applied to the data. Best fit for the curve. Is it a linear regression? Is it nonlinear? What nonlinear model fits best? And so on and so forth. Unlike the ANOVA, regression methods apply when explanatory variables, sometimes called independent variables, are continuous rather than discrete. Another method, ANCOVA, analysis of covariance. A final method which should be mentioned is applicable in the general context of the analysis of variance, but applies where there are additional explanatory variables, often continuous variables still, which may have an effect on the experimental outcome. So you may have heard of results of these where we held this, we normalized for age and then compared this and that. Right? So there might have been a covariate that would be contributing, so if you normalize to that, it should help to eliminate the variance contributed by that variable, and then you test to see how everything else varies once you stabilize that one, in essence. So in theory, such variables should not be affected by the specific treatments conditions in the study. So that's what I said, age was one that is sometimes used. For example, in a study with a single baseline measurement and then multiple measurements during a treatment period, may wish to adjust our analysis for the basis of any difference between experimental units present at baseline. Age, as I said, gender is another example. Stage of the menstrual cycle if you're examining only human females. For example, this is accomplished by considering the baseline measurement as a covariate and performing an analysis of covariate on the resulting data. Such covariate adjustments can be important for two reasons. First, they help to eliminate or minimize any potential bias caused by differences in the covariates, which themselves are assumed unrelated to treatment. Second, the ANCOVA methods often provide increased power relative to unadjusted methods as they reduce the unexplained variation in the study. And again, remember when we talked about confounding factors way back in the beginning, variables that might account for what we're observing or might contribute variance that cannot be explained. So here's that unexplained variance. So I'm going to end there with one final review of our choosing a test. We have our scales, the continuous, ordinal, discrete. Is it a normal distribution or not normal? The not normal distribution or the ordinal and discrete data are evaluated by non-parametric measures that we'll talk about in Module 2, Lecture 10. After we've talked about two-way analysis of variance for normal distribution, more than two equal variances, use the analysis of variance. Unequal variance, we talked about how that shows up in some of the ANOVA tests. Might send you over to run a non-parametric evaluation on the data. So we now understand the types, the scales of data: continuous, ordinal, discrete, normal versus non-normal distribution, the correlation, where there's one group and two variables that you would look at. If there are two groups, is it paired or unpaired, using the appropriate tests in each case. And if it's more than two, and equal variance, using the analysis of variance. So now, hopefully you feel much more comfortable and confident in how you use statistical analyses to evaluate your data. And this completes our discussion of Module 2, Lecture 9. I appreciate your attention and time. Thank you.